It is not so very long since humankind first set foot outside Africa. Our story has been a story of the long, slow colonisation of the world over thousands of years, of discovering new lands and learning to live in them. Just as the ancient maps of the world were slowly filled in as we explored, so our closest stars are beginning to be mapped out. We know that our galaxy is teeming with planets. We've been detecting them since October 1995. We now know that around 1 in 10 Sun-like stars are orbited by planets. But could any of these worlds support life? Could mankind ever take the next step? Could we cross the vast distances between the stars to explore or even colonize these new worlds? Are we forever confined to the Earth? Or could we ever become a truly galactic species? Before we can even think about travelling to planets around other stars, we have to find them. The stars are just pinpricks in our night sky, so far away that light itself takes years to reach us. Any planets orbiting them are invisible, even to the most powerful telescopes. So how can we even know what's out there? Tim O'Brien researches astrophysics at the Jodrell Bank Observatory, home to one of the world's most powerful radio telescopes.
Well, there's a number of methods that are used for discovering planets around other stars. The most successful one, really, the one that's discovered most planets so far, is a thing that we might call the Doppler Wobble technique, and that relies on the fact that, as you were probably taught in school, that the sun sits still at the middle of the solar system and all the planets orbit around it. And in fact, of course, that's not true. Like many things you're taught in school, that isn't true. What actually happens is that if you can imagine a situation where you take the sun and you sat it on one end of a seesaw, and you say took the planet Jupiter and sat that on the other end of the seesaw, what would happen would be that it would tip. The sun's a lot heavier than Jupiter, so it would tip up. If you sort of took the point at which you balanced that seesaw and you moved it closer and closer and closer to the sun until it balanced, you'd find actually, if you work out the numbers, that that point's just outside the surface of the sun. And if you took that seesaw now that's balancing and you spun it around, then Jupiter would sort of orbit in some sort of biggish circle, and the sun would actually orbit in a very small circle like that. So the sun would wobble by about the size that I'm illustrating there. So if the size of the sun was this big, it would wobble by about that much due to the motion of Jupiter. So we can't actually see these distant planets around other stars. They're too faint, too far away, but we can see the stars.
The gas giants detected were massive and very close to their stars. They had to be in order to cause a detectable shift in the star's position. That made them inhospitable places. Their atmospheres thick with poisonous gases. The pressures, temperatures and gravities make life as we understand it an impossibility.
Jupiter is 1,899 times the mass of the Earth, but Jupiter is, we know there's plenty of Jupiters existing around other stars. Earth is a remarkably small little planet, but it has the properties which allows life to evolve on it. So the problem with going from how many planets do we know exist to how many Earth-like planets are there, we have to ask, well, the problem being is that it's difficult to discover low-mass planets.
To detect Earth-like worlds, another, far more sensitive technique was needed. When the solution came, it not only allowed scientists to detect much smaller planets, but also had the potential to tell them something far more surprising.
There's another technique called the transit technique, which is basically an eclipse. So it's when, if you can imagine the star sitting here and you can imagine the planet orbiting around, it could well be that we're looking at the system in the plane of the planet's orbit. So every one period of the planet, if it was the Earth, it would be every year, and the planet will pass in front of its parent star. If you measure the brightness of that star, then what you see is its brightness just dip, just slightly, and then come back up again. And that's because of the light being blocked by the planet as it passes. Now, you know, interestingly, that gives you a bit more information as well, because it actually lets you estimate the size of the planet, because you can look at how much of the light was blocked. And perhaps even more excitingly, some of the light that from that star is actually going to pass through the atmosphere of the planet, and you can actually look for, therefore, for signatures of the composition of the atmosphere in the spectrum of light from the star.
When you look at an extrasolar planet, what you're looking for is gases in the atmosphere that cannot be there simply as a result of chemistry alone. If you find an atmosphere, such as the Earth, with 21% oxygen, then you know that that concentration of oxygen can really only be properly associated with biology.
By analysing the changes in light from a star as a planet passes in front of it, scientists can work out the composition of its atmosphere. And from that information, they can deduce whether the planet harbours life.
I think if somebody showed me a spectrum of light from one of these extrasolar planets that fitted the same pattern as the Earth's atmosphere spectrum, which is indicative of the presence of life, sure, you know, you might well say, given everything we know, chances are there's life on that planet.
Our telescopes aren't yet powerful enough to detect the signatures of life on other stars. But within just a few years, they will be.
If you have separate telescopes, individual telescopes separated over a large area, you get the effective resolution, the resolving power, the ability to see fine detail, the same as a telescope, a single telescope, which has the diameter of the most widely separated of these individual telescopes. There are proposed space missions which will fly in formation a number of telescopes, optical telescopes, which will all be looking at the same object at the same time. They will be separated by large distances, which you can achieve in space, and they will all be sending their individual signals to a central telescope or a central processing satellite.
The European Space Agency has one called Darwin, and NASA, the Americans, have one called Terrestrial Planet Finder. We will find a planet like the Earth, you know, probably within the next 5 years, actually. So there'll be options there for a planet the size of the Earth in its habitable zone. Maybe in the next 10 to 15 years we'll find evidence that there's spectroscopic evidence that there's signatures of life in the atmosphere of that planet. That'd be the sort of planet you'd want to visit, I suspect.
I think that this is possibly, and you know, it's easy to over-dramatize, but I really do think this is one of the most profoundly exciting periods in the history of biological science, and maybe even in the history of social science as well. Because for the first time, I think, really during the next 1 or 2 decades even, we will be in a position to find out whether there is life on other distant planets, or whether in fact we're surrounded by a desert of dead planets.
I would argue that the question of whether we're alone in the universe is one of the most important questions that there is, and that there has been. And of course, it's a question that's been, you know, investigated by philosophers, you know, through the ages. It's now a question which we're actually on the, you know, we're on the borders of being able to answer.
But this analysis will only give us a tantalising glimpse. The moment we discover the possibility of another world, teeming with life light years away, we're almost certainly going to want to know more.
The most tantalising thing will be that if we find a planet with oxygen in its atmosphere, we really won't be able to distinguish between the possibilities of that coming from microorganisms producing oxygen, or a planet that also happens to have an intelligent civilization. So that would, of course, be the next stage in the challenge, is to find out what is producing this oxygen.
5, 4, 3, 2, 1, and liftoff of Space Shuttle Atlantis to assemble the framework for the science laboratories of tomorrow.
Houston now controlling.
After our Sun, the closest star is Proxima Centauri, and even that is over 4 light-years away. The distance is unimaginable, and nothing our technology has built so far could get us anywhere near it.
One of the problems is really the velocities which we can reach with current technology, and the space shuttle has a maximum speed of about 6 miles per second, and a fairly straightforward calculation shows us that to reach the closest star would take over 100,000 years.
Taking aim on the International Space Station for docking on Friday.
But interstellar space is not uncrossable. Technologies are beginning to emerge which offer the possibility of shortening travel times from millennia to just a few decades, or even less. In 1973, the British Interplanetary Society set a group of scientists and engineers a theoretical challenge. The group was asked to design a rocket which could get an unmanned probe to Barnard's star, some 6 light-years away, within 50 years.
The question was posed as to if we wanted to send a probe to another star, how could we build such a probe given our current understanding of science, or a reasonable extrapolation of that?
The idea was that a young scientist watching the probe's launch would be able to monitor the results of the experiment before he retired. The scale of the challenge was huge. But by 1978, a spacecraft design was put forward. It was named Project Daedalus.
They needed a craft that they could boost up to at least 1/10 the speed of light.
The ship's tiny payload and huge fuel tanks would be driven forward by a series of nuclear explosions.
It effectively ignites a series of very, very small, miniaturized hydrogen bombs behind the craft.
The proposed craft was to be a 2-stage rocket. The first stage would power the spacecraft for 2 years, accelerating it to 7.1% the speed of light and using up 46,000 tons of fuel in the process. These huge engines would then be jettisoned into space. Stage 2 would then kick in, boosting the now much lighter craft up to 12% of light speed. After 2 more years, the fuel from these engines too would be exhausted, and the ship would coast for the rest of the journey before deploying a series of probes as it sped past its target. The key idea behind Daedalus was that the project did not require any new advances in science. The scale of the engineering would have been huge, but the technology was all in place. If we wanted to do it, we could. One proposed fuel for Daedalus was helium-3, a very rare isotope, but one with great potential for producing safe, clean nuclear power. At the time of Daedalus, the prospects for mining helium-3 were limited, but recent discoveries on the Moon have ignited a renewed interest in space travel.
1.1 million tons of helium-3 has been found on the Moon, and this is now motivating, if you like, a second space race. Humans are going to walk on there by 2020. The Americans and the Chinese both declared this. Other nations are slowly following. So the prospects for going to the stars in my view, have just got a little bit closer.
But the scope of Daedalus was limited. The theoretical mission wasn't manned, and crucially, when it reached its destination, it wasn't designed to stop.
To slow down at the end requires a lot more fuel, because you've got to accelerate that fuel to 1/10 the speed of light to start with. You're not going to be Captain Kirk and still look young by the time you get to the next star system if you're using nuclear fusion.
The limitation on the speed of any rocket is the weight of its fuel. 99% of the weight of Daedalus would have been fuel. If there was a more efficient fuel, the craft could be smaller, lighter and faster. And there is. Antimatter.
Well, there's a famous phrase about antimatter, which is 1 gram of antimatter will get you to Mars in 1 month. That's how much energy potentially can be released from antimatter.
Antimatter is made up of atoms of ordinary matter, with their electrical charges reversed. It's not science fiction. It occurs naturally. A large solar flare creates about half a kilo of antimatter. It's even been created artificially, here on Earth.
Certainly in the 1990s, the CERN laboratory created something like 9 anti-hydrogen atoms in a small-scale experiment.
Releasing huge amounts of energy from antimatter is easy. In fact, it's too easy. That's the main problem.
There are severe issues with having to manufacture antimatter in the first place, and of course it's very difficult to store, because as soon as antimatter touches any ordinary matter at all, it will annihilate and explode.
For interstellar travel, the best solution is thought to be a massive power station orbiting close to the Sun. It's by no means an easy option, but this could generate the quantities of antimatter needed for a long journey at very high speeds.
If you could combine a fusion fuel with, say, a matter-antimatter, potentially you could get to very high fractions of the speed of light, of the order of 99% even. But these are very much theoretical concepts, but certainly plausible.
But with great speed comes other problems. According to Einstein, mass is related to velocity. In other words, the faster a spaceship moves, the heavier it gets. But there's an even stranger effect. In 1971, scientists placed an atomic clock in a commercial airliner on a flight around the world. When the clock landed, they compared its reading with an identical clock at the United States Naval Observatory. They found that the clock from the plane was now slow by around 40 nanoseconds. By travelling faster through space, it had experienced a slowdown in time. A spaceship travelling at close to the speed of light would experience a far greater time dilation. Its occupants would age far more slowly. But even if the practical speed limit for any spacecraft is a little less than light speed, there are still thousands of stars close enough to be explored. And it is very possible that ships like this will be the vehicles making our first journeys to them. The beauty of the ships which carried the first humans across the oceans was their simplicity. The elegance of their design meant that these craft were cheap to build, easy to maintain, and carried no fuel. Could interstellar craft ever be designed on these principles? A spaceship leaves Earth orbit. It will travel at 1/10 of the speed of light, and yet it has no engines. Instead, it will rely on a surprising property of light.
The fact that light can push matter, that was established by James Clerk Maxwell, the Scottish physicist, back in the 19th century. and was first experimentally verified by Peter Lebedew, a Russian physicist, about 1900. So this effect has been known for well over 100 years.
If you can create and unfurl a sail which is large enough, light enough and thin enough, the light from the sun will do the rest.
If you can imagine, again, 40 by 40 metres of this type of film, which is then carefully folded and packed in a very small volume. To deploy the sail film and to keep it flat, to keep it in tension, then you need a structure. So for example, you need, say, a boom which can be rolled up into a coil and then will automatically unfold itself into a rigid structure, and at the same time pull the sail film out and keep it flat.
The sun's effect on the sail is tiny, far less than the weight of a feather, but it is constant, so the sail can continue to accelerate for years or even decades.
The fact that the solar sail doesn't require any propellant, then it can do either very high energy or very long duration science missions, which are either difficult or impossible for conventional propulsion. Perhaps starting with doing sample return missions to comets or asteroids, working out to going to the very edge of the solar system, and then beyond and stepping into interstellar space.
Our ship's destination may be deep in space, but its initial heading is straight into the heart of our solar system. In fact, this ship is about to make the most dangerous manoeuvre of its journey. It makes its way directly towards the burning sun.
As the sail falls inwards towards the sun, gets closer and closer, then the pressure of sunlight on the sail film is increasing all the time. And if the sail can pass very close to the sun, but maybe 1/3 of the distance of the Earth from the sun, it gets a very significant push from sunlight, accelerates as it passes close to the sun, and then essentially heads off in a straight line directly away from the sun out to the edge of the solar system.
Solar sail theory is simple and well established. The challenges are now simply in engineering.
The key problem with solar sailing is how do you package something which is maybe the size of several tennis courts into the volume of a domestic fridge, launch it into space in a very, very harsh environment, and then ensure that the solar sail can reliably unfold itself without human intervention in space.
Real solar sails are currently being tested for missions within our solar system, and it's only a matter of time before the first probes are launched using this technology.
Two experiments have been done. There was a European solar sail deployment test, which was using composite carbon fibre booms with a 20-metre sail. There's also a test in the United States, again of a 20-metre sail with a slightly different technology for the booms, but that was deployed in a large vacuum chamber to simulate the space environment. Both of those tests were completely successful, so there's a high degree of confidence that a real solar sail would reliably deploy in space.
However, the further you want to go, the faster you need to travel, and long-range missions require much larger sails.
Well, to get to true interstellar space, you need to take your science payloads about 200 times as far from the sun than the Earth is. At that point, the sun's magnetic field kind of dissipates and you get into true interstellar space. To get there in about 25 years, you would require a very large disc-shaped sail, perhaps about 300 metres across, to take a 200 kilogram spacecraft. But it's really scratching the surface in terms of the distances to the nearest stars. To get to Alpha Centauri, for example, is about 1,400 times further on. For doing real kind of interstellar missions, then the sail would typically be the order of several kilometres in diameter.
But a light sail isn't limited to getting its power from the sun. A giant space-based laser could be focused on the spacecraft from Earth orbit, pushing it even faster.
You can imagine beaming power direct from the laser to the solar sail across vast distances. And this would mean that as the sail moves away from the sun, it's being continuously pushed by the laser.
The power of this laser would need to be huge.
A conventional nuclear power station will produce a few gigawatts at most of power. So if you can imagine that scaled by a factor of at least 10 or 20, and all of that energy being put into one laser device, then that gives you some idea of the types of laser power which would be required.
But in space, the sun itself could be harnessed to provide the energy for it, giving the sail an infinite source of power throughout its journey.
You can build very large and very lightweight sails, and you have the infrastructure of tens of gigawatts of laser power, then yes, there is nothing to stop you sending a spacecraft to the nearest stars.
Colin McInnes believes getting to the stars is not about scaling up. It's not about building larger and larger sails or bigger and bigger engines. It's about scaling down.
I think we will go to the stars. I don't think we'll go in person, not for a very long time. I think we will send our sensors there first, embedded in silicon or carbon. That may be through laser push light sails or some other form of propulsion. But I expect the first interstellar starship, if you like, the payload won't be some 10,000 ton starship. It will maybe be a couple of kilograms of nano-engineered material. A 1 kilogram microspacecraft, or perhaps of this size, would require a much more reasonable engineering proposition to build, to pack, and then to deploy in space. So if you have to deliver 100 metric tons to Alpha Centauri, then clearly that's going to require a colossal vehicle to deliver it there. If all you want to deliver, though, is a kilogram of nano-engineered spacecraft, then the scale of engineering required to deliver that becomes much smaller. So I suspect in the future that we'll see advances not so much in propulsion, but in miniaturizing payloads.
Whether we travel by nuclear fusion, antimatter, or solar sailing, one thing is for certain. The journey is going to take a while. If we ever want to launch manned missions, interstellar travellers can expect to have to survive in the icy darkness of space for years, decades, or even centuries. Here on Earth, our life support system is the entire planet. The challenge for the space traveller is to replicate that system in miniature.
It's a little bit like driving a long distance cross country, let's say across a desert. You know that when you get there, you can get some local resources and you can live off materials that you can get from the local environment. Whereas when you're in your car driving, you have to take everything with you and you have to think about what you need to take. You have to plan it, and it also has to be very robust. You're in interstellar space, it's probably completely dark apart from starlight, there's no water around you, there's no soils to grow food in, and there's no gas to make air from. So everything that you need has to be inside that spacecraft. That's very different from the situation when you get to your extrasolar planet, when you could use local resources to essentially live off the land.
Learning to live for long periods in space may even give us clues about protecting our own environment on Earth.
You can grow food even in an enclosed spacecraft, and for something like a mission to another star system, the lengths of time that you're talking about are just so vast that you have no choice but to consider how to recycle every atom of every resource that you've got inside that spacecraft.
If you can recycle efficiently enough, and can generate power for light and heat, then the size of your engines becomes less important. If life on board is sustainable and comfortable, then it doesn't matter how long the journey takes. The travelling lifestyle is not alien to humans. We have made long journeys throughout history, setting out across deserts, oceans and glaciers. The early travellers had little idea of what to expect, and often small groups would have had no contact with outsiders for generations. We evolved as a nomadic species, and it may be this heritage, as much as anything else, that compels us to look to the stars now. However, the crew of an interstellar mission may have to commit to a lifetime of travel, not only for themselves, but perhaps for their descendants as well.
In terms of a psychological challenge, this is going to be like nothing that people have ever done before. And even ancient journeys on ships from one continent to another simply don't compare to the psychological challenge that these people will face in travelling to another star system.
And it's not just the journey that will be tough. We're unlikely to find our new planet as hospitable as the Earth. But this is a one-way trip, so we will have to do more than simply get to our destination. We will have to live there.
So when you land on the surface of another planet, whether that's in our solar system or elsewhere, you need to establish some basic requirements for human beings. And it's all the same things that you're familiar with in your home. You need fresh water, you need food, you need an atmosphere to breathe.
Since you're intending to colonize, you need to take your life support system along with you. And if you're aiming for a biological life support system, you'd have to have some kind of ark on board containing plants, many different strains of bacteria that can be used to make soil.
What you need to do is to establish an artificial ecosystem, if you will, on the surface of one of these planetary bodies.
And the first trials for creating such an ecosystem have already been done. Between 1991 and 1993, Charles Cockle spent 18 months working in Biosphere 2, a massive experiment attempting to create an entire independent, self-sustaining ecosystem.
Biosphere 2 was an experiment in the deserts of Arizona to attempt to create a completely closed life support system, if you will, for people to live in. But it was much more than a life support system. It had a rainforest, it had a savanna, it had an ocean. It was in some sense a miniature Earth packed into a giant greenhouse. Biosphere 2 was a success in the sense that it was probably a very good lesson in the difficulty of building a completely enclosed and highly complex life support system that involves many different types of ecosystems.
After scientists had spent 14 months living in Biosphere 2, eating, breathing and drinking only what was created within its domed walls, cracks started to appear in the project. Food began to run low. Oxygen in the air dropped to dangerous levels due to microbes in the soil, and many of the animals and insects within the dome died out. The psychological stresses on the team also began to show, and after 2 years, the experiment ended in acrimony. But Biosphere 2 was a very complex ecosystem. A colony on another world would be much simpler.
The fact they had these different ecosystems all interacting made it far more complex than the sort of life support system that you could get away with if you wanted to put, say, 10, 20 people, even more people than that, on the surface of another planet. I think it is possible to build an independent base that's completely separated from the Earth and grows its own food. You just don't need to go to the complexity of Biosphere 2. You want something that's quite simple, has very few connections in the food chain, and is predictable and can be manipulated relatively effectively by small numbers of people. Although the machinery is quite complex, it needn't necessarily be that large. You can build a base for, say, 7 people out of 6 or 7 modules, maybe of 2.5, 3.5 meters in diameter, which are connected together, and one of these modules would have a growing area where you can grow some plants that you might eat as part of your diet. Another one of these modules might have an atmospheric extraction system, say on Mars, to extract liquid water. Another system might be set up to split that water by electrolysis and make the oxygen that you need to breathe. So the complexity is quite high, but the volume is not necessarily that great. And you start off probably with some sort of plan as to which plants you are going to grow, and you would start off with a plan that was very robust and simple. You tested over and over again on the Earth, put it through different catastrophic failures to try and understand its sensitivity and to try and build a robust system that can provide food and provide your oxygen needs as well. And then you would take along a lot of other plants, maybe some other seeds that you could add to this, and start to build up your complexity as your confidence in handling the system improved.
The colony would grow organically, from a small group of 10 or 20 people into a whole society.
Once you start to think about a society, then you're moving into a much larger scale of complexity in terms of building life support systems. But there's no reason why you shouldn't just scale up quite simple life support systems. You simply have different habitats with different greenhouses and different crops being grown, and those modules can be independent, but they can also add a certain sort of robustness and diversity into the whole system that makes any one system's failure unlikely to affect the whole system.
But a colony in a greenhouse would be difficult to sustain. Wouldn't it be easier to find a world where we could simply live outside?
The one thing we've learnt over the past 13 years that we've started to find exoplanets is that there's a vast variety of them out there.
There might be a planet out there that's got oxygen in its atmosphere, that's breathable to human beings, where there's liquid water on the surface, and where you could land without any alterations to the atmosphere and just walk around and breathe, and maybe even plant crops. I think what you'd have to worry about is if there was oxygen in that atmosphere, it would imply that there is life already on that planet. Human beings are not very good at deciding not to colonize a lush green new pasture when it looks like somewhere they can colonize. We've been down this road many times throughout human history. The results have usually been catastrophic. They may have been good for the civilizations that conquered these new lands, but they've been catastrophic for the civilizations that were there already. We should have learnt something from that history by now, and one of the things that we should have learnt is that if you find an extrasolar planet with 21% oxygen in its atmosphere that looks like it was produced by life and might even be capable of supporting intelligent life, you don't go landing there, establishing colonies and setting up bases before you've done your homework in trying to work out whether this is a planet that might actually be best left alone because it has its own biological trajectory.
After all, we wouldn't want it to happen to us.
Imagine tomorrow a group of astronomers were using their space telescope, let's say the Hubble Space Telescope, to study the outer regions of the solar system, and they detected a fleet of inbound spacecraft from an alien race who had detected the Earth and its 21% oxygen atmosphere using an extrasolar planet searching telescope around their own planet, and like us had decided this was actually quite a good place to colonize. And they had no ethical qualms about this at all, and they were coming in to colonize this planet regardless of what sort of life there was there. I don't think we'd be very happy. In fact, I think we'd be extremely scared and we wouldn't know what to do about it. We certainly wouldn't have very good ethical thoughts about this, and I don't think we would agree that it was within their rights to come and land on our planet, destroy us and take up residence here. And that's really the ethical quandary that we should consider for ourselves.
But there is another way. It involves biological engineering on a massive scale. But many scientists believe it would be possible to terraform an empty planet, turning it from a barren, lifeless world into a new Earth. There have already been detailed proposals drawn up to terraform Mars, But that planet is not the best candidate. With a galaxy of planets to choose from, future colonists could afford to be a lot more picky.
You'd want the world to have its own inventory of water. You wouldn't want it to have too much water either, so you'd want both ocean and dry land. An ideal world that didn't have life on it would be, say, like a very early young Earth.
Simply introducing bacteria to such a planet would kickstart the process of creating a breathable atmosphere. After perhaps 200 years, the atmosphere would have started to become less harsh.
Even at that early stage, even though you don't have a breathable shirt sleeve environment outside, you don't have to wear a spacesuit, and you might be able to adapt some of the bacteria you grow outside into something edible anyway.
Eventually some hardy plants would be seeded, and as the atmosphere became stronger, insects would be introduced. Photosynthesis would start to fill the atmosphere with oxygen.
Now, okay, to produce an atmosphere that would be breathable to humans with just photosynthesis, it might take as long as it did on Earth.
Producing an oxygen-rich atmosphere more quickly would require a lot more direct intervention. But scientists, like Charles Cockle, aren't waiting for a launch date before starting to plan their expeditions.
I think that it will not be long before one could actually start to think about industrial processes for humans to live on extrasolar planets. All we actually need is data that tells us about the atmospheric composition of extrasolar planets. Because even if we have extrasolar planets without oxygen in the atmospheres, we can still think about ways of turning those atmospheres into breathable atmospheres. For example, let's say we found an extrasolar planet with carbon dioxide. Well, we know how to crack carbon dioxide, break up the gas to make oxygen to breathe. So as soon as that data starts coming in within the next decade or two, telling us about the atmospheric composition of other planets orbiting other stars, we'll be in a position to actually dream up industrial processes that would allow people to live on the surface of those planets.
After all, reforming the environment of an entire planet might be a huge undertaking, but it doesn't require any new scientific breakthroughs.
It's a question of scale, not a question of physics.
If humans do manage to cross the vast distances between the stars, if we do settle planets far from the Earth, if we do eventually become a truly galactic species, with our homes on many worlds, will these worlds always be tiny, isolated islands, with even radio signals taking years to pass between them? Einstein tells us they will. His equations forbid anything from travelling faster than light. However, physicists working at the edge of our understanding of the universe are beginning to come to a different view.
What we want to be doing is discovering ways to travel at A, appreciable fractions the speed of light, or B, to surpass the light speed barrier. Of course, we've got Einstein's theory, which tells us that nothing can travel faster than the speed of light. But there's a fortunate loophole in this idea, in that the expansion of space itself isn't limited by this restriction. Things traveling through space have a speed limit of the speed of light, but space-time itself can travel at arbitrarily high velocities.
The idea of a warp drive has been around in science fiction for years. But could it ever be a reality? In 1996, NASA funded the Breakthrough Propulsion Physics program, a study designed to look for answers to that very question.
First time I tried to think seriously about the warp drive was at the end of the 1990s in the United States, when NASA started a program called BPP, standing for Breakthrough Propulsion Physics. So I was a member of this effort. It picked up contribution from all kinds of scientists, but especially physicists, experts in relativity and quantum physics, just to find out whether or not it might be possible to have a warp drive.
Kelvin Long organised a conference at the British Interplanetary Society at the end of 2007, at which physicists from around the world met to discuss the physics behind faster-than-light travel.
There was a paper in 1994 by a chap called Miguel Alcubierre, who basically showed that in general relativity, that superluminal speed was possible.
The warp ship looks quite unremarkable for a spaceship. Its engines are sufficient to get it around the solar system, nothing more. The design is spherical, in order to be incredibly compact, because the way this ship travels, every cubic millimetre of its volume comes with massive energy costs.
You imagine a ship and it's surrounded by what we call a bubble of space, and you want to go from A to B. So you've got two ways to do that. You can either, the vehicle can move from A to B across space, which means it has to accelerate, which means you get special relativistic effects, and it takes time. The other way to do it is to make space come to you. In other words, the distant objects. So there's a planet, and it's 2 light years away, and you want to get there. You collapse space in front of you, so you drag the object towards you, if you like. And behind the spacecraft, you cause it to expand behind you. So essentially the vehicle is able to go from A to B, not by moving across space, but by making space itself move through the vehicle by collapsing and expanding. And it's this collapse and expansion and the rate of that which propels the vehicle forward.
The ship enters the warp generator, a massive ring in space, capable of generating huge amounts of the negative energy needed to produce the warp bubble. The ship is now disconnected from our space. It cannot on its own start or stop its journey. Further out in space, launchers are used to set off the expansion and contraction of space, which will transport the vehicle. The theory behind this impossible sounding method of travelling without moving is sound. However, there's a serious drawback.
Current line of thinking is that there are vast amounts of energy required to generate these necessary warp bubbles. I think some of the original calculations indicated that you would need more negative mass energy than was available in the entire observable universe.
It's possible that these enormous energy requirements could be reduced as scientists learn to understand the universe better.
People have developed other mathematical constructs which demonstrate that warp drive constraints aren't so harsh and perhaps of the order of 10 to the power 33 joules negative energy. That's still enormous.
These ideas are based in orthodox physics. There's nothing unorthodox about the physics that they're based on. And if anything, firstly, we should approach this from the angle or the perspective of this is a good tool to get young physicists and young scientists interested in the field. And once they're interested in the field, it's also a good learning tool. So I think that's really the perspective that we really want to be coming from. And anything positive that comes out of it is a bonus.
In my view, it's at the earliest hundreds of years away. I don't feel like our state of knowledge in science is mature enough, qualified enough to say that you could never do warp drive. But at the moment, the problems suggest it is prohibitively difficult.
By 2002, NASA's funding for the Breakthrough Propulsion Physics program was removed.
After 9/11, The Americans put more money into the military than in the space research, and this clearly is a kind of research that is not going to produce something practically immediately, okay? But nevertheless, the good point is that the group of scientists that were trying at that time to make the effort are still in touch with each other. So regardless of whether we meet in America or we meet in Europe, as we are doing now here in London, the good point is that we keep in touch and we try to make some progress.
But this area of study is so new that there may well be other solutions to the problem waiting to be unearthed.
Most of us, if not everybody of us, is stumbling in the dark, you know, because all this is brand new stuff. Anyway, my personal opinion is that I am not sure that the general theory of relativity by Einstein is absolutely the best tool we have at the moment. There might be different way of building the warp drive. We don't know. We have to dig more deeply in the calculation. But this is just to mention the possibility that something else outside relativity or beyond relativity might come into the place. The bottom line is also that, of course, at the moment we don't have a single theory merging relativity on one side and quantum physics on the other side. They are still very much separated. So sooner or later, some kind of synthesis will have to be discovered and applied.
So, it is still possible that a sufficiently advanced society could create the means for faster-than-light travel. When it reaches its destination, our warp ship's bubble will have to be collapsed, allowing it to switch to a local travel mode. It opens out to allow the crew to move about. Traditional engines kick in to fly the craft to its destination. The settlement of space is a huge challenge. The undertaking is vast. But the technology to detect planets around other stars is here already. The ability to detect life on these planets is just a few years away. We can even see ways to travel to distant stars and to set up colonies there. But how will the first journeys be made? Indeed, given the difficulties facing civilization here on Earth, should we even try?
I think we have to find ourselves a noble purpose that makes our civilization great and something worth working for. Expanding out into space, settling other planets, exploring the universe, and establishing our species as a spacefaring civilization that spreads across the universe is an extremely exciting and productive way for humans to direct their energies.
If we were, as a society, if we were to abandon space travel and space exploration, we would immediately become inward-looking and navel-gazing. And history shows that when that happens, civilizations begin to crumble.
I think the first trips to the stars will be a combination of propulsion schemes. There will be robotic explorers. Obviously, we're going to go to the planets first, and then humans will follow. And I think eventually we will go to the nearest stars, and it will be robotic explorers using a combination of fusion, matter-antimatter, plasma drive type propulsion schemes, which can get us there in a moderate time, maybe of the order of a few decades. I think that will happen. Certainly, if not this century, the next century, that will definitely happen.
Periods of exploration or periods of a blossoming of culture, a blossoming of civilization, and also a blossoming of economic growth and well-being in society. So to me, space exploration, space travel, and its ultimate limit in interstellar travel is a natural extension of that. And if we were to abandon that aspiration, then I have no hope for the future of humanity.
Either the population stabilizes, which is what probably politicians would like to achieve, but they were not able to achieve so far. Or, for the long future, we can envisage migrating to another solar system. In the meantime, we keep the dream alive. So we still, I mean, we the physicists, the mathematicians, and the scientists, you know, we do the calculation. We try to understand as much as possible with the very limited computers that we have at the moment. And we hope for the best.